Okay, for this lab we were given the model of a weight tied to a spring, and since we can say that a rope is many tiny springs that can be represented as one spring, we will use that idea later in this lab. So the forces acting on our system are gravity and the spring force, and we were asked to find the changes in kinetic energy, gravitational energy, potential energy, and the total energy in general. So the physics, or like the equations we use in this lab, were Newton's second law, where the final position equals the initial position plus average velocity times change in time, and final velocity equals initial velocity plus F net over mass times delta t. And the second fundamental principle we used is the energy principle, where the change in energy equals zero if the system does not interact with the surroundings, as in the surroundings do not do work on the system. So change in energy equals kinetic energy and all the energies in the system. So they are not each energy is not zero, but they cancel out to give us the final change in energy, which is zero. So here's our system that we are modeling as we tracked it in Tracker. We track the XY positions and put them into a CSV file to be used later in the Python model, and we use the graph here to find the time interval between each oscillation, and we use that to find the constant, since t squared equals 4 pi times m over k, where k is our constant. And onto the coding. We plugged in our givens. Mass of the ball is 0.402. The initial position from Tracker, we plugged that in. Initial velocity is 0. We started at 0. Started at rest from 0. And the delta t between each frame is 1/210, given by our camera. Gravity is 9.8 meters per second. We calculate k using the equation I just gave, and the relaxed length of the spring is 0.123 meters. Then comes the more important part where we plug in the equations and so the final length is the ball position minus the spring's position. Then we get the unit vector for length, which we use later on, and S, the stretch, is the final length minus the relaxed length. And then we get the energies in Python. The kinetic energy is half mv squared, represented by that equation. Potential energy is mg, change in height, position y. And the spring energy is half k times s squared. The k we got and s we got from up there. Then we plug in the gravity equation, negative mg, the spring equation, ks times the L hat we just calculated, and all the forces acting on spring, as I said in the introduction, are the spring force and the gravity, so those two are here. Then we use Newton's second law in the last two equations to get the final velocity and the final position. This is the code I used to find the changes in energy, where delta k equals k minus k initial, and delta ug equals ug minus u initial, and delta us equals us minus us initial. Then we plug in this code to graph all of these changes in energy. So when we run our final code, it predicts the motion of the system, where the blue arrow is the spring force and the black one is the gravity force. And here is the graph, or the plot of all the changes in energy, where the spring force and the gravity force cancel out, and kinetic energy keeps moving up and down. So kinetic energy plus potential energy equals 0. So the shift happens here, as you can see. And none of the energies are 0, but they all cancel out together to be 0. So that's why the yellow line is just constantly equals to 0, since no other outer system interacts with our system. The surroundings don't exert a force on our system, which satisfies that. Finally, here is the motion prediction of the system, where the blue line is the system, and the red line is the model, and they line up almost perfectly. The minor discrepancies due to air drag, which we did not account for in tracker, and if we sub in the y for the x in tracker and track the x position instead, it will come out almost the same. Thank you.